Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. In the last class, we started the finite volume technique and we derived the state update formula. So, basically instead of using the values at the grid points, we basically created cells, okay, and stored the value at the cell center. Okay. And the state update formula we got was something like if you have a cell centered value which is so this is our cell I. Okay, these are my faces I plus half, I minus half, and this is the next cell I plus 1, this is the cell in the left, this is I minus 1, right. So, the state update formula that we had was basically if you want to get u I n plus 1, which is basically I want to get the cell average value at the next iteration, was u I n, okay, minus delta t by delta x, okay, f I plus 1 half, okay, and minus f I minus half n, right. Of course, the problem that we are trying to solve is del u by del t plus del f by del x equal to 0, right. And we stop that the only question that we have is that how to calculate this I phi plus half and I phi minus half, which which results in another question is that how the u is varying. So, f I plus half is nothing but f calculated using the value of u. Okay. So, if it is Euler equation, u is basically what you have rho u and rho e, right, in the conserved variable form, right. So, this is basically f evaluated at x I plus half, right. So, if you know how the u varies within the cell, we will be able to calculate, right. Similarly, if you want to do f I minus half, that is f value of u at x I minus half, okay, or in another way this is u x I minus delta x I by 2, right. So, in general, let us say if you know the gradient somehow, this del u by del x, that how the u is varying, okay, within the cell, then you can evaluate at any point of time. So, let us say if you want to get it u I plus 1 half and x, so you can use this if you know the value at cell center which is u I n, and plus let us say somehow you know the gradient how the u is varying, okay. So, from cell you have to go to the face, okay, this cell to this face, okay, this is I and this is I plus half, okay, I n, and this is x I plus half minus x I, right, and you calculated that, right. So, you need this gradient how it is varying within the cell. Now, there are many ways you can basically think how your value is varying within the cell. So, one is like using the constant value, okay. So, let us say that I have 3 interfaces, okay. So, this is 1, this is 2, and this is 3, okay, and you have basically the cells here, okay. Okay, so one thing you can say that okay, within one cell the variation is just uniform, okay. So, that means you have constant value. So, in this cell you have got a constant value, let us in this cell, let us call this I minus 1 and I plus 1, okay. And we are saying that my variation within a cell is constant, okay. So, whatever value we have at the cell center, same value we are having at everywhere in the cell. Okay. So, this is one value within the cell, the other one, let us say in this we have some value, this is ui plus 1, this is ui. Okay. So, this is I have no variation. So, basically it is constant. Okay. And last one is okay. This is how it is varying in the next cell. Okay. So, you can see that if you are using a constant variation, so that means your value is not changing within the cell. So, at the interface, so these are the interfaces. Okay. This is the interface, this is the interface, this is the interface, this is the interface. Okay. So, this is between I minus 1 and I, this is between I and I plus 1. Okay. So, you have some value of the flux coming from the left and some value of the flux coming from the right. Okay. This is a problem because you are saying that so what is flux? Basically it is what is basically going across a face, right, or going coming in across the face from the next cell, right. So, you have something smaller going out and bigger coming in, right. So, the flux should be constant at the face, which is not happening here if you are assuming a fixed variation, no variation within the cell, basically the constant value, right. Similarly, at the next one also, okay, here also you have one value from the left and one value from the right. Okay. What you need is a constant value, the value at the flux is constant, right. So, what you can do, you can assume a linear variation, okay, which is what actually works in most of the basically finite volume. So, let us say this is my value here and this is the value here. Okay. So, one variation is here, okay, and similarly you can have another variation which is from here to here. Okay. So, this is basically the value is linearly varying. So, this is the linear variation within the cell. Okay. So, that you are getting a constant value at the interface. Okay. It will be linearly varying, but you will be getting a constant basically fixed value at the interface. Okay. So, this is how basically your variation will look like. Okay. You will have something coming here, something coming from the right, and you have to basically make sure that you use a formula, so that your flux is whatever you are calculating from left and right is basically the same. You have to use the values from left and right and calculate the flux. Okay. So, you assume the linear variation, you can also assume the quadratic variation. That means, let us say that you are from within this cell, okay, let us say in I minus 1, your variation is something like this, okay, or something like this. Okay. So, you can use quadratic or cubic, but that will result in basically some problem in the formalism. Okay. Some of the properties that you want to preserve in the finite volume, as you will see in some time. Okay. For example, the positivity or the conservation, they will not be obeyed when you assume a quadratic or higher order variations here in the finite volume. Okay. So, the linear variation you can choose and you can basically march it. So, basically if you know the linear variation, you can calculate this du by dx, right. So, that your du by dx value, yeah, if you have the linear variation, okay. So, you know the value at I plus 1, you know the value at I minus 1, you this can be bar, okay, and this is your delta x, the distance between I plus 1 and I minus 1, and you can calculate the gradient here. Okay. Of course, there are more sophisticated way of calculating the green Gauss, calculating the gradient. You can use the green Gauss or the least square. I am not going into the details there. So, basically if you have the problem which is 2 dimensional or 3 dimensional, this simple formulation of calculating the gradient will not work. Okay. You can basically, if let us say if you have a triangle here, okay, and you want to calculate what is the value on this face and this face and this face, okay, the gradient. So, this is my u bar I, and you want to calculate this u bar I at this face, let us call it f1, okay, ui f2 and ui f3. Okay. So, how do you go from this point to this point, right. So, one way is like you use the green Gauss theorem to calculate the gradient here. Another way is that you basically write it. So, you have neighboring cells here. Okay. So, and you have this neighboring cell centers. So, you write your gradients, you write your formula u I equal to, let us say if it is u j plus delta u by del x j and delta x j. Okay. And you try writing for this also and this also. Okay. And you will have del u by del y j, del y and delta x j. Okay. So, you write for all of these directions and then you take a least square, because you have more number of equations than the information that require. You require only 2 gradients, del u by del x and del u by del y in 2D for example, but you have many cells neighboring it. If it is a quadratic element, you will have 4 cells neighboring it, right. So, you basically write it and you try to get the best value of del u by del x by using the least square. I am sure you might have read about the least square, where you calculate the error, okay, and then you see that in the L2 norm how you can minimize the error. Okay. So, without going into the detail, if you becomes the 2D and 3D, you have to use these two schemes are very popular, okay, for the reconstruction. One is the green Gauss, another is the least square. Okay. So, now you got the gradient this del u by del x, okay, and you can calculate the value of this, let us say u n x I plus delta x I by 2, right. So, this is my I and this is I plus half, right. So, this will become u n x I plus del u by del x, okay, at I and basically delta x I by 2, right. So, if you want to calculate the value of I 5 plus half, you can take the gradient and use the value of u x I and calculate that, right. The other way to do it is basically take the value of u I plus 1. Okay. So, you have a cell I plus 1 also. Okay. So, you get from the right side. Okay. So, x I plus 1 minus delta x I plus x I plus 1 by 2. So, this is delta x I plus 1 and this is delta x I. So, by 2, because you will have face on the left also and face on the right also. Okay. So, this is another way to get that. So, and the last one is you can take the basically average of this, what you calculate from the left and what you calculate from the right, and just take the average of 2. Okay. So, this one is very equivalent to the central differentiation scheme, okay, on a uniform grid, but this is as we have seen that for the kind of convection problem, this is not stable. So, this option is usually not used. Even if you are using this, then you have to use some kind of limiter. Okay. Basically, it is to make sure that the value does not go very high, okay, and you have to basically limit the value. Okay. So, we can use one of these two schemes, and that depending on what kind of direction you have, like you recall that when we had c greater than 0, okay, we had used this FTBS, okay, backward step, backward in space. When we had c less than 0, then we had used FTFS, okay, but we respected the direction of propagation and accordingly with the scheme. Okay. So, similar idea comes here also. So, if it is c is greater than 0, the flow is going from left to right, you can use this is f I plus half and this is f I minus half. Okay. So, you can use the first choice, which is basically calculating from the left to right. Okay. Basically, it is kind of the backward stepping. Okay. If it is I plus 1, you calculate from I plus 1, then it is a forward stepping, right. So, this way you can calculate the f I plus half, this is the way you can calculate the f I minus half, okay, and then you calculate the value of the u I n plus 1. So, this is how the finite volume works. So, ultimately you got all of the elements that you want. Delta t, delta x is fixed by your grid, delta t is based on the similar CFL criteria that we had for the finite difference. Okay, same rules that we had, for example, if you want to use the explicit formulation, the most cases the CFL number is less than 1, the same kind of approach will work here also. Okay. And calculate the fluxes I plus half and I minus half, update it and you can get the value. Okay. if you go to 2D, the slight trick that we have to use, okay, because you have more directions here. Okay, we have del u by del t plus del f by del x plus del g by del y equal to 0. Let us see in 2D. Okay. So, in 1D what we had done, we had just taken this integrated it across a volume. So, this gave us this f I plus half and f I minus half. Okay. If you go to f I plus half and I minus half. Okay. But if it is 2D, okay. So, you have two directions, for example, this is I and this is j. Okay. So, we need to introduce the concept of volume. Okay. Instead of distance in each direction I and j, we will rather put a cell volume here. Okay. So, you have the cell which defines the 2D element in this particular case. So, what we can do, we can write this as del u by del t plus del dot f is equal to 0, and like we did for 1D, we will use in 2D also, we will use the integration in each cell, right. So, now it is del u by del t plus del dot f equal to 0, we will integrate it around the cell, right. This is no longer 1D. Okay. So, this omega I cannot be delta x I. Okay. So, you can take it 2 part del u by del t omega I, this has to be multiplied by the small volume, right, because we are integrating the omega and plus del dot f d omega equal to 0 omega I, right. Now, this part is easy, right, because you can again use the same assumption that my cell centered value is basically the average of the entire value in the volume, right. So, if you use that, you can write it as del u bar by delta t, and you will have maybe some delta omega, okay, the cell volume. Okay, we can just call it omega. Okay. How do we convert this one so that we can make use of the phases that we have, right. So, I am sure you must have read in your calculus that there is a famous theorem called Gauss divergence theorem. It is also known as the Green's theorem. Okay, I think there is some difference on the textbook. Sometimes when you convert from 3D to 2D, they call it Green's theorem, 2D to 1D, they call it the divergence theorem, right, but it is all the same. Okay. So, what it says is that if you have a value, any value, okay, let us say this del dot f, okay, which is around a volume, okay, you can basically write it in terms of the f dot n dA. Okay. So, this is your Gauss divergence theorem. What does it mean physically? Let us say, let us try to understand it. Let us say this is your volume, okay, and there is some divergence here, the del dot f value here, and you want to integrate it across this volume. Okay. So, what you can do that instead of integrating across this volume, you can just see that what happens on the faces, right. So, you can just use so this is my normal, let us say this is my normal in this direction, this normal in this direction, okay, this is the normal in this direction, this normal in this direction, right, and normal is outward. Okay. So, you can see that the fluxes that we have at the interface, okay, that f dot n, you basically quantify here, okay, and then you quantify here, then quantify here and quantify here, and basically integrate it across the area, and that will be the same value as you have like if you want to calculate as del dot f in the entire volume. So, we converted our information in the volume to the information on interfaces, the faces that we have. It can be done for the 3D also in the triangle also, right. So, let us say if you have like this, then what you can do, you can use it like this. Okay. So, that way you can basically calculate. This is f dot n. So, if you use that, so you can write your formula like this. Okay, here of course, this d omega. So, this is called area normal. Okay. So, what I have done, I have taken area as a vector. So, which is nothing but, so your f dot n dA can also be written as f dot dA, right. What is a dA is basically it is an area normal vector. So, now it is a vector which represents the area in the normal direction. Okay. So, now there is no approximation till now. Okay. Now, what we can do is that you this is in integral form and we are using different shell volumes, right, triangles or rectangles or quadrilaterals, different kind of things, right. So, you basically go across all the faces and add this value. So, you can change this integral sign into the summation sign, okay, where j is the number of faces. So, you go to each face, calculate this f dot n, multiply with delta s area on that, okay, and keep on adding across all the faces. Okay. And finally, you will get this state update formula, du by dt is equal to 1 by omega I f delta j delta s j. We have the same problem now. The delta s j is defined using our geometry, okay, the kind of mesh element using. Only thing that we need to calculate is the f perpendicular j, which is the interfacial flux. Okay. And as we discussed that you have to define how the variation of the u is across the cell, and if you assume the linear variation, you can calculate the gradient del u by del x, del u by del y in this particular case. Okay. And then from that you can calculate the value of u at the interface. Once you have the value at the interface, you can calculate the flux at the interface. Okay. And you can use either Green Gauss or the least square to calculate the gradient del u by del x and del u by del y. Okay. This is just the representation of that. This is delta s in this case. So, because this is your face, so this is the information of delta s, you keep on multiplying on each side. Okay. And this omega is basically the area inside this entire domain. Okay, that is the omega. You can see that here there are 1, 2, 3, 4, 5, 6, 7. Okay. No, there are 8 faces, right. So, you can use any kind of element, okay, and you will basically be doing the same conservation that we have been doing. Okay. So, yeah, because I talked about the conservation, let us talk about what is conservation and why it is important. Okay. So, this right hand side is called the residue, okay, and if the problem is steady state, then this will go to 0, that means your du by dt is going to 0. Okay. And if it is not a steady state, okay, then this will keep on changing, okay, and that change in the interface, okay, reflects that you have basically non-zero del u by del t dx, okay, this information. Okay. So, it should only depend on the boundary term. Let us see if we are doing the same thing in our finite volume. So, we are doing this del u by del t dx, and we are doing it across each cell and add it up. Okay. Let us say you have some elements like this, okay, very complicated element. Okay. Of course, there are consideration that your grid should not have very high aspect ratio, because then let us say your aspect ratio is very high. Okay. Let us say this is your cell, okay, and if you have the cell center defining here. Okay. So, of course, in one direction the variation is very high, right. So, this kind of cells will create problem. So, there are some consideration when you are trying to make a grid. This kind of cells will have problems in basically getting the convergence, okay, or it may blow up also. Okay. So, of course, those considerations are there, but let us say that you are calculating this du by dt dx, and you have this 0, 1, 2, 3, 4, 5, 6, let us say you have 10 elements, right. So, you can consider it across each of the volume, okay, this volume, or each of the volume, and sum it up, and you can see that across each volume you can write it del u by del t dx as del f by del x dx, right. So, you can write it across each of them, but del f by del x dx. So, this is I mean 1D 2D it remains the same, Okay, it is basically this is I plus half and I minus half. This is f I plus half and this is f I minus half. What is the difference in the flux? Okay. So, for a given cell, so you take any cell, okay. Let us say I am taking this cell, this particular cell, okay, and you want to calculate this du by dt dx omega 0, okay. So, that will become across each, so this will become f perpendicular j delta s j, okay, and for all j, and it will become negative, right. So, basically we will loop over all the faces and calculate the changes that is happening in the interface. If it is 1D, then you can just see that, oh, okay, this is my I plus half and this is I minus half. You just have to consider the difference there, right. So, what you are doing is basically whatever changes it is happening inside the body with time delivered by del x is basically depending only on the boundary flux for that particular cell, right. In this case it depends on all three phases, in 1D it depends on only I plus half and I minus half, right. That means you have the local conservation, right. So, we want to ensure that my du by dt is only depend, it should only depend on the interfacial flux on the boundaries, okay. So, that is what is happening here, that you are getting a local conservation, because you can see that it depends only on I plus half and I minus half, right. If you integrate it also, okay, let us say that I want to do it for the entire domain, right. So, this will be see if we can write here, okay. So, this value, for example, this will be let me write in 1D because this is easy to explain. So, this is basically f I plus half minus f I minus half, okay, and then you will have basically I plus 1 by 2, this is I plus 3 half minus I plus 1 half, okay, and plus you will have f I plus 5 half minus I plus 3 half and so on and so forth, right. So, all these terms will get cancelling out, okay, and what you will ultimately get is basically f n plus half minus f minus half, okay. That means, if you have a domain like this, okay, so this goes from your cell center, this is my cell center 1, okay, and this is my cell center n, so this is my n plus half, okay, and this is my f minus half, okay, this is the first one. So, if you integrate the values of fluxes everywhere, all the second terms, I mean here it will be for this cell you will have these phases and these phases, okay. For the second cell you have this phase and this phase, so this term will cancel out, okay, and similarly you will have n minus 1, so this will cancel out with this one. So, ultimately what will be remaining is minus half and n plus half, okay. So, for the entire domain also the du by dt depends only on the boundary fluxes. That means, you are having the global conservation, okay. So, you are basically having both the local conservation and the global conservation in the finite volume. This is not true in the finite difference formulation, okay. Finite difference formulation, in some cases depending on what kind of boundary conditions you have, okay, you may get the global conservation, but not the local conservation, okay. Maybe if you are using a uniform grid, okay, then you may probably get the global conservation, because as we have discussed that you have this collapse of the terms inside, we have discussed in the finite difference when you use the conservative formulation so you will get this global conservation, right. But in general it is not true in the finite difference. Similarly, if you are using a boundary condition, let us say some kind of Dirichlet boundary condition, let us say the wall boundary conditions, again on those boundaries you do not have this conservation being applied in the finite difference case, okay. In the finite volume case we apply it even on the boundaries, okay. So, the conservation is guaranteed in the finite volume, both the local conservation as well as the global conservation. Now, the last point that I want to cover today is that why is conservation important, right. So, typically what you have is you talk about the consistent scheme. right. So, what do you mean is basically let us say you have a scheme which gives like del F by del H plus order h to the power n, okay, which is basically the nth order scheme, and as the h tends to 0, it will basically approximate your whatever value, whatever true value you have. Okay, let us say my true value is delta f. Okay, so it will approach to that value as h to 0. So, this is there in your finite difference also. You have to look at the scheme which is consistent. Okay, now most of the schemes are derived through Taylor series, and we found that they are consistent schemes. So, if the consistency is there, then why, and if you are using the proper stability criteria, then you should be happy, right. So, why you need conservation, right? Why conservation is important in finite volume? So, you will see its importance typically when you have fluxes, when you have shocks, right. So, if you have a shock, so you know that there is a large jump in the values. For example, if this is pressure here, the pressure on the right will be very high compared to pressure on the left. Okay. So, here there is a sharp discontinuity at this point, right. Your variables may have very different value across the shock, but the fluxes will be unique, okay, even at the shock, okay, if you have a conservative scheme, right. So, if you are not having that, okay, so then what will happen that if you do not have the conservation scheme, then you will get something called the artificial source or sink in the computational domain, and that will basically make the shock behave in a very different way, which may lead to be non-physical shock, okay, or basically shocks with wrong strengths or at the wrong location, okay. So, the shock conservation schemes or shock capturing schemes, what they do, that they ensure that the conservation property is obeyed there, okay. So, that is why the finite volume is a very good approach if you want to resolve shocks, okay, compared to the finite difference approach, because finite volume approach by default basic guarantees conservation, okay. So, what we learned today is that even in 2D or in 3D, we can use the similar approach as 1D in terms of finite formulation of the finite volume. What you need to do is to use the Gauss divergence formulation, write that del dot f in terms of the f dot n. So, basically fluxes, normal fluxes at the interface, sum that up, that will give you the total change in fluxes across the interface, okay. Take it on the right hand side, that is your residue, and use your favorite time scheme on the left hand side, and basically get your state update formula, okay. That is one thing. Second thing is that your finite volume guarantees both the local conservation as well as the global conservation. So, that is a very good thing, especially if you have flows which has got strong discontinuities, because despite of the fact that the discontinuities at a given location, your fluxes will remain constant, okay. So, that is what your conservation says, okay. So, we will look into more detail about finite volume. We will solve some problems, for example, the convection diffusion scheme or even the Sox tube problem in the next class. Okay, with that I will stop here. Thank you very much.